Today, our main discussion would be about understanding acid and basic strengths. Although we already gone through these cases in GOC, it's better we learn it once again, especially regarding amines and carboxylic acids. Okay, first let me give you all the strength based on amines. Okay, basic strength of amines, basic strength of amines and nitrogen groups. Starting with first, if you start with the simple cases here, so in case if at all I have NH2 here, NH2 here this way, okay, one is aniline, one is, cyclohexyl amine. In that case, basic strength mainly depends upon localization and delocalization. So this is localized electrons, this is delocalized electrons. Second case is when you have aniline here and similar aniline group is present with some NO2 on it. So if NO2 was present here and NO2 was present here and NO2 was present here at ortho, meta and para position, in that case, obviously NO2 is withdrawing at all the positions. So just hydrogen would be better as compared to that of ortho, para and meta and para. Within that, meta is relatively better than para than ortho. Okay. Ortho for two reasons. It is also called ortho effect, as well as it is due to the strong hydrogen bonding that it will make with this one. Okay. So remember that due to, right, ortho effect and hydrogen bonding. Hydrogen bonding. What is happening here is due to hydrogen bonding, the hydrogen here and oxygen here will make a bond by which the lone pair will make much better resonance as compared to that of what we had it without, NO2. Got it? So for a better hydrogen bonding here, you will notice that this will have, hydrogen bonding. That's how it will be. And now you see, uh, in fact, if you notice this case, okay, suppose where you have NH2 with two NO2 groups here, this will have such strong hydrogen bonding with hydrogen here that lone pair is not available. Lone pair is not available at all for base bonding, and this will be hardly a base. Correct? So does not dissolve in acid. Does not dissolve in dilute acids. That is an indication that it does not dissolve in dilute acid is an indication that there is no lone pair available here. Correct? In fact, if you take this case here, we do not consider if you have here, we do not even consider that as a base. Okay. See, this is called picramide, and not a base. You can imagine how strongly the hydrogen bonding will influence. Next case is SIR effect. SIR effect. Okay. That is, if by chance I have N with two methyl groups here, and then I have NO2 here, right? And if you have one NH and this one, and lastly, if you have only NH2 here. In this case, this would be strongly basic. because due to methyl and NO2, these two will have van der Waal repulsions. Due to repulsions, this nitrogen and these two methyl groups will turn into out of the plane situation. When they become out of the plane, the lone pair does not make any resonance. So whenever you think about SIR effect, you should always remember that there should be some group on nitrogen. If there is no group here on nitrogen, please do not apply SIR effect. Simple. Okay. Only if there is an some group on that, apply SIR effect on it. Here, everybody. Other cases. Suppose if you have like this with methyl, two methyls are present here like this. Okay. And I have one methyl present here. Then I have no methyls present here. Okay. In this case also, the basic character, if you notice, that will be more for the first one, second one, third one. Please do not apply anything like ortho effect here, okay? Because the dominance is always about SIR. More amount of SIR, more is the basic medium, basic nature. Second, if I take this case, similar case now, this time I'm trying to decrease this situations here. This is how it is. Now, if at all I start removing one methyl here like this, and here it is NH2. In such cases, order would be exactly reverse now. Got it? This will be the basic strength. This time you are applying because here in NH2 with two methyl groups, only when there is NH2, remember everybody, only when there is NH2 you can apply ortho effect. What is ortho effect also I'll tell you, but meanwhile understand that this is ortho, this is due to ortho effect, this is due to SIR and this is due to SIR. Okay, sorry. So basic strength will be the reverse of it, like this. Okay. So this one will be more basic than this one, than this one. So more the ortho effect nature, less is the basic character. Got it? I hope everybody understood this logic, how to apply SIR effect in all of these cases. Okay. Next one, bread sugar. Okay. That is, if you have anything like ethyl and double bond O, and the same thing I'm comparing when you have a bridge to form here. Obviously, this lone pair is involved in resonance, but this lone pair cannot be involved in resonance. Again, this is delocalized, this is localized. Okay. So whenever we have a localized and delocalized, this will be the strong basic compound. Okay. Sixth one, if you notice, aromaticity. Aromaticity. Aromaticity decreases the basic character drastically. So if you compare this group H with N here like this, and then we have NH here like this. Okay. In these cases, if I take this as A, B, C, now this is extremely weak, nature of as basic, because the lone pair is always involved in resonance. Therefore, if you notice the basic character in such cases, C will be more basic, then B, then A. Okay, remember between C and B, compare hybridization. Okay, and A is aromaticity. If we compare aromaticity, that will be the least basic in nature. I suppose this part is clear everywhere. Okay, next. If you have plus and minus efforts, that is, in case if I have N here like this and O here like this, N lone pair and H. So you would see that These methyls are actually supporting nitrogen by plus I, while these methyls are going towards oxygen. So basic character will decrease. This is due to minus I of oxygen. Due to minus I of oxygen. Another example on a similar line, if you notice, you will see nitrogen present here like this, okay, on a bridged position, and similarly, one more nitrogen is present here like this. Again, when it comes to the nitrogen here, one nitrogen is pulling over the other. So because of that, if you compare these two lone pairs here now, this lone pair is less basic. So again, due to due to minus I effect of nitrogen. That is, so do not think like there are two lone pairs and it will be more basic and so. No, it is not the case. Okay, I guess this part is clear, everybody. Seventh one, if you notice, plus M and minus M effects. Notice plus M and minus M effects. That is, in case if you have aniline with aniline at a group G, this is what I need to compare. And G group is NO2, chlorine, OCH3, OH, and CH3, right? And H. If these are the cases, then basic character depends upon whichever is most donating towards benzene. The most donating in this case will be OH, then we have OCH3, then we have CH3, then hydrogen is better than chlorine, then NO2. Okay, this will be the order. This is due to plus M or minus M effect or even hyperconjugation. Those kind of effects, whenever you keep it, that will be more basic in nature. Okay. Next, eighth one, due to ring flipping. Ring flipping need to be applied only when you have straight chain versus bicycle. Okay. So that is N ethyl, ethyl, and ethyl with a lone pair here, while same type of ethyl groups if they are connected in a bicyclo format. Now, this lone pair is not getting flipped anywhere, but this lone pair will keep flipping above and below. Okay, so this will always keep moving above and below, because of which the availability of lone pair is weaker, but here it will be better. This is due to lone pair. Okay. Next one is d orbital resonance. D orbital resonance. In this case, if you notice CH3 thrice N, if you compare that with SiH3 thrice N, okay. Now here there is a back bonding happening between lone pair of nitrogen versus silicon, so that is not available due to back bonding from nitrogen to sulfur. Nitrogen to sulfur, there is a back bonding, because of which you will see this nature. Clear, everybody? And lastly, ortho effect. Ortho effect. Ortho effect is also known as SIP, steric inhibition of protonation. Got it? That is, if you have NH2 with some group Z, any group Z, okay, due to Z, okay, basic character will be less than basic nature of aniline decreases. Basic character of aniline will decrease. Okay. So now, if you apply this logic to all cases first, okay. Now, why does this SIP happen here? Let me show you the logic first. Suppose if you have NH2 here and CH3 here, Well, you can say, sir, there is a repulsion between these two because they are bulky groups on both ends. Well, there is, but the lone pair for that reason is actually it appears to be available. It appears to be more available. But as soon as it takes the H plus here, as soon as it takes the H plus here, now it will become NH3 plus, which is way bulkier. Now that will become much more bulkier. Due to this bulkiness, this space of NH3 and this space of CH3, they both will have strong repulsions. These clouds will have strong repulsion. Because of these strong repulsions, this is an unstable, unstable or less stable conjugate acid. This is a less stable conjugate acid. Being a less stable conjugate acid, right? This will be reluctant to accept this H plus. So if it accepts H plus, it is becoming an unstable conjugate acid. That's why this group will be reluctant to take this H plus. And this phenomena is called steric inhibition of protonation. Got it? Which means if there is any bulkier group on ortho position, definitely we will have less stable, conjugate acid. Therefore, the amines will be very, very less basic in nature. Okay. Therefore, if you compare any cases now let us see case by case. Suppose if you have NH2 versus, okay, if we take, let's say, CH3 at ortho, meta, and para position. Okay. If I take this way, then what is the effect you will see? See, at para position, you will have hyperconjugation also and inductive effect also. That's why para is better than meta. But now hydrogen is better than ortho. Why? Because of ortho effect. Now this ortho is because of ortho effect. That ortho effect is because of steric inhibition of protonation. Got it? Same way, if at all I take the next case here, let's say I take one more case here as some withdrawing group here, COOR, ester. Same logic here also. COR is a strong withdrawing group, and most withdrawing position is at ortho, and that will be least basic. And hydrogen will be more basic, then meta, then para, then ortho. Okay. Again, the logic fits there. Similarly, if you have any halogen also, let's say there is chlorine here, in that case also, it is withdrawing at all positions, but from hydrogen. Then now, when it comes to halogens, we'll always follow inductive effect. So para will have least compared to meta, and ortho will have the most. Okay, next. Next, I can apply the same logic to NO2, and I can say we have discussed this NO2 case already. So here we can say this is hydrogen greater than meta, greater than para, greater than ortho. Okay. Now, if you recall, here the reason is ortho effect as well as hydrogen bonding. So therefore, intra-edge bonding, intra-edge bonding contributes to ortho effect, contributes to ortho effect. Okay. Now, where ortho effect should not be applied. Okay. So when it comes to OCH3, here with OCH3, in case of OCH3, now ortho effect should not be applied. You will apply like a normal cases only. OCH3 is a donating group here, right? So in that case, obviously at para position it will be the most, then hydrogen, then ortho, then meta. Okay. So it is not like we have to apply the same for, just like how ortho effect is, we should not be applying that way. So definitely it will be better than meta. Okay. And yeah. Okay. Because overall OCH3 is donating group on benzene. It is not withdrawing, it is donating group on benzene. Okay. So I hope all of you understood in which cases we need to apply this. Just a minute. Check out the exact value once. Yes. So can you explain those CSP case once again? Yeah, once again. I'm doing the same thing. I'm just putting out the exact data also. Right, this is right. Check. See, Vidal. What I'm trying to say is that at ortho position, because of its bulkiness, we might apply the ortho effect. Okay. Due to ortho effect, we expect that the ortho should have the least basic nature. But problem here is, even though it has ortho effect, it is still a strongly donating group via resonance. Via resonance, it is still a strongly donating group. And that's why it will slightly dominate over its ortho nature, and therefore ortho would still be strongly basic than meta. Okay. Suppose this is clear, everybody. Is I'm audible? Anyone, please confirm. I'm audible. Okay.
Yes, sir.
See, beta, what I'm trying to say is that OCH3 will be we are expecting it to give ortho effect, right? What do you mean by ortho effect? Just go back here. If there is a bulkiness, OCH3 is sufficiently bulky as well. So it is supposed to give ortho effect. It is giving ortho effect, but at the same time, because of its lone pair, it is also giving plus M effect. You remember, plus M will increase the basic character. So, but between those two, plus M is dominant when it comes to OCH3 or OH. That's why that will be more basic than meta. Clear on that? Right. See, let us go to the next point here. The next type of cases other than ortho is guanidine cases. Guanidine cases. Guanidine cases, these are, you know, strongest bases. For example, if you have double bond NH, NH2 and NH2. Because if you see there are three lone pairs, this lone pair will be involved in resonance, this lone pair will be involved in resonance, this plane lone pair is localized. This is localized electron, this is delocalized, this is delocalized. Okay. So imagine if H plus will make an addition here. So this will become NH2, and here it will remain NH2, and here it will remain NH2. This will become NH2 plus, and this NH2 plus will become resonating structures which are equivalent to each other. We can see here that plus charge will keep moving around at three different locations. One double bond here with plus charge, one double bond here with plus charge. What are these three? Equivalent resonating structures. And you know that if we have equivalent resonating structures, okay, if we have equivalent resonating structures here, so in that case, you will notice that this conjugate acid is extremely stable. So if conjugate acid is very much stable here, that means this is a very, very strong base. So out of all organic bases, this is the strongest, base of all the organic compounds. Okay? And therefore, if you compare anything with guanidine, so that will always be more basic. So that means if I compare strongest of the bases, like for example, I consider this as one of the strongest bases as well, which is in the bridged form. And this, if you compare with anything which is methyl group also, I have a methyl here, and I compare this as ABC. Then if you notice the strength, still A will be much stronger than B, than C, because C is also have gonadine system, because there is a lone pair here, there is nitrogen here which will support it, so it will still going to give you equivalent resonating structures. So A, C and B, so this will be the case. So you could imagine these kind of gonadine systems will make very, very strong basic nature. Okay, I hope this logic is clear to everybody. Okay. Anudeep, I'll explain in a bit better. Okay, let me finish this. So I hope all of you understood this logic. Okay, how exactly it is going to be. I hope all these cases are clear. Right. Next, C, basic medium, right? Basic medium when it comes to aqueous solution. Okay? In aqueous solution, right? It all depends upon which particular group we are talking about. In aqueous solution, when it comes to R being methyl group, okay, then it is 2 degree greater than 1 degree greater than 3 degree greater than ammonia. Okay, what I meant to say is like this, that is CH3 twice NH is greater than CH3 NH2, which is greater than CH3 thrice N greater than ammonia. Okay? The factors that are making this to happen is solvation, solvation and inductive effect. So because of these two effects, acting together, the more appropriate order for basic character is 2 degree, 1 degree, 3 degree and amount. And by chance, if R is C2H5, if R is C2H5, in that case, the order would be 2 degree, 3 degree, 1 degree, and then NH3. Okay, this will be the order. Clear? Now, to put all groups together, like what if you have ethyl and methyl to compare with each other? So, overall comparison, I'll write down here. Overall comparison. So, if you see the overall comparison, you will see diethylamine in aqueous solution. Everything I'm writing is in aqueous solution is better than triethylamine is better than dimethylamine is better than ethylamine, which is better than methylamine, which is better than trimethylamine, which is better than PHCH2NH2. Okay, benzylamine, benzylamine, which is greater than NH3. Okay, this is again issue. Students would feel that phenyl is actually withdrawing in nature. So how is this going to be more basic than NH3? Again, this is all in order according to the active solution. So please keep that in mind. Then uh, pH and Me twice, okay, with the lone pair on it. And then we have pH, NH, Me with a lone pair on it. And lastly, pH, NH2, which is aniline. Aniline will be the least basic, correct? So please make sure that you are aware of this order. Everybody, please check this out once. If you have any doubt in here, you can ask me. Oh, just go back to this case once again. Where is that? Here. Check. Between these two beta, when you discuss about uh, 5 and 6 here, aniline, if you are comparing that with OH group here, NH2 and OH, okay? In these cases, see, oxygen and hydrogen has hydrogen bonding. Here also hydrogen and oxygen has hydrogen bonding. So because of which there is a ortho effect. Definitely that is influencing. But how much it is influencing is not enough for meta position. So which means if you compare the overall basic nature, it is still going to be para, okay, then aniline, then ortho, then meta. Right? So for these two cases, you got to understand that basic character of ortho position is still going to be lesser than that of aniline form. Okay. See the next case. If we compare, next, see, here we check out all the various examples in this case. Now, first one, suppose if you have CH3CN and CH3C double bond O NH2, and we have aniline here in this case. Okay. So if I take this as ABC, Between these three, definitely the least basic. Okay, because of sp hybridized nature. Here we always need to check out based on hybridization. So cba. Okay, next one, if you have nitrogen, this one, with again nitrogen with a double bond O. Okay, and if you have a bridged structure like this. Okay, and if you have bridge structure without any double bond O. Okay, so now I have A, B, C, D. Yeah. So in that case, definitely no double bond O means that will be uh, definitely better basic compared to that of C, compared to that of I mean this is D compared to that of C compared to that of B. This will be the order. Okay. Amides are extremely weak bases, so you can easily judge on them. Next, if you compare uh, pyridine versus aniline versus pyrrole here. So pyroles are extremely weak. So if I take this as A, B, C, then A will be better than B than C. This is an exception. Between A and B is an exception. Although NH2 is sp3, it is delocalized electrons, because of which basic character decreases, while aniline will have more basic character here. Fourth one. Right. So next, if you apply NH2 with this one, where is that? Uh, yeah, let us apply on this case now. This nitrogen here, this way, and six membered ring of nitrogen here, hydrogen, and a pyrrole case like this, and a pyridine case versus N and H. So A, B, C, D, E. Now check this. What is the correct order in these cases? I have a five membered ring and a six membered ring. Okay. And then we have three membered, four membered. Then we have delocalized and sp2 and an sp3 carbon. What could be the correct order? See, generally, if you compare uh, three membered, four membered, and five membered, in that case, always five membered will be more basic, then four membered, then three membered ring. But between five membered and six membered, it is the five membered which will have more basic nature. Now, if you compare the basic nature here, A will be more basic than B for sure, and B will be more basic than E because of the minus I effect. And after this, D will be more basic because it is localized. C will be the least basic because it is delocalized by aromatic nature. This is a very important case, everybody. Please let me know if you haven't understood anything here. Another case as a note, you can check it out, that in case if you have three membered ring, which you call it as aziridine, that will be less basic than four membered ring, acetadine, that will be less basic than this one. This is pyrrolidine. Okay? Aziridine, acetadine, and pyrrolidine. Got it, everybody? See the next case. Next case, if you have again comparison of pyrrole pyrrole having a group on it. Okay, pyrrole having a six-membered ring on it like this, and then we have pyridine, comparing that with piperidine. This is piperidine. A, B, C, D. Check and try to get the answer. What is the correct option for that? Similarly, if I take NH2 and I have double bond NH and I have double bond NH with NH2 and I have double bond NH with NH2 and NH2. A, B, C, D. Check out in the fifth case what we should get here. In case of fifth one here, okay, you would notice that fourth will definitely be most, basic. So D, correct. After that, we will see third one because that is localized. Okay, between A and B, it is delocalized. But you see, this aromatic nature is being shared here. So even if the lone pair is not involved, imagine if the lone pair is not involved, correct? Still, sorry, if the lone pair is involved here, this lone pair is helping this to get, you know, resonance stabilized here, correct? That means aromatic nature. This lone pair is the one which is pushing to satisfy this ring as well as satisfy this ring as well, correct? Because otherwise, if this pi bond is present here and it is making aromatic ring here, correct? In that case, the issue is going to be uh, where is that? See, if you talk about this lone pair, imagine this lone pair is involved in resonance here, correct? If it is an aromatic resonance, this resonance is a consequence to help this double bond. Or let me put the other way, this pi cloud will be always involved in resonance with this one. So this ring will try to become anti-aromatic. So it will force this lone pair to always get involved in it. Okay. So whenever these kind of benzene groups or anything that are connected to this aromatic ring, to satisfy them, they have to involve the lone pair even more strongly. So that means it will be A greater than that of B. Everybody understood this logic? Right. See the next one, A, B, C, D. In this case, what we can say? We can say D is a gonadine form. Definitely, it is more basic than C, and then A, then B. Here, it's purely based on hybridization. This is sp3, this is sp2 hybridization. Clear? Next, if you have NF3, NH3, and M, Me twice, and N, H, and N, Me thrice. See, if nothing is mentioned, suppose if this is nothing mentioned, like it is acidic, polar protic solvent, water, aqueous solution, or non-polar, you will always by default take it as an aqueous solution. So if it is an aqueous solution, what will be the order? Tell me. If it is an aqueous solution, I take this as A, B, C, D. Then the order has to be C greater than D greater than B greater than A. Check if anybody has a issue with that. Next, if we have a gonadine form like this NH, NH2, and CH3, right? And then we have, sorry, N here with NH bonded here with a lone pair here, and then NH bonded here the lone pair here, double bond and double bond with a lone pair here. Okay, and then finally double bond NH, NH2 and NH2. Okay, so A, B, C, D. If you notice, all of them are gonadine forms only. And the most stable gonadine is the last one because it will have three equivalent resonating structures. So D is the most basic one. And after that, which one? First one, which is, you know, open chain with a donating group. CH3 is a donating group here. See, between A and B, the issue is this NH, this group, it is gonadine in this system, but from the other end, this is actually withdrawing via inductive effect, while CH3 is donating. That's why A will be better than B. Now, between B and C, if you notice, B and C, C is the least basic because this lone pair also, although this is a gonadine system, the lone pair here will be involved in aromatic nature also. Okay, because of which the gonadine nature will decrease. The gonadine nature will decrease here. Okay, that's why this is going to be more basic. Everybody understood why B is more basic than C? Next one. Suppose if you have aniline with aniline and NO2, methyl and methyl group here. So methyl and NO2 group here, right? And then I have aniline with one NO2 group here, then NH2 with NO2 and NO2 group here with methyl here. So if you have A, B, C, D group, then check out which one is more basic. See, all of them have withdrawing groups, and aniline does not have any withdrawing group. So that makes aniline has the more basic. Okay. Then, if you notice the second case, because of the SIR effect between these two, all will remain, non-planar. Because of the non-planarity, these groups will not involve in resonance. So they are weakly withdrawing. They are not strongly withdrawing. They are weakly withdrawing. Okay. And one end you will notice methyl is supporting here, donating by uh, donating via what do you say, inductive effect and hyperconjugation, which is not done by NO2. So you will notice that this B will nullify that effect which you get it in C, because C will have only minus a effect of NO2. But imagine like this NO2, this NO2 is getting cancelled, while between these two, methyl is still a slightly dominant position, because of which B is more basic than C. And obviously, D will be the least basic because of ortho effect. Everyone clear on that? Please check. Any doubt here? Right, that's all you need to merge from the basic strength cases. Okay, let me, uh, we were discussing something on this. I got the data exactly. Let me show you. Ah, for aniline case, this is right. That is, when it comes to OCH3 case, this is right. Only in the case of OH, this has been found. The data shows that ortho is slightly greater than aniline form. Ortho. So here it is. Here, any kind of effect is not applied, whether it is hydrogen bonding, whether it is SIP, right? Because OH is smaller in space, it is smaller in nature. So this is the order. So this is the only exception you will find. So please make a note of that. POHM in the case of OH. And everybody. Now let us go typically. Let us go back typically to the carboxylic acid cases. Okay. In case of carboxylic acid cases, there are few things which are given in NCRT that you need to check out and learn it. See, carboxylic acids. The carboxylic acids, first, which is the stronger withdrawing group? Very important, and this is given in NCRT only. Check. Phenyl is relatively weaker than iodine, then bromine, then chlorine, then fluorine, then cyanide, then NO2, then CF3. If this is how the order is given, which means if you have CF3 COOH, this will be strongly withdrawing compared to CCl3 COOH. Okay, clear? And sorry, NO3, NO3, CH2, CH2, NO2, COOH greater than CH2, Cn greater than COOH, and so on. Like this, we need to check out the acidic character. Clear? The first case is clear, everybody. Okay. Next. So what if we have CF3 COOH, that will be better than CCl3 COOH greater than CHCl2 COOH greater than uh, NO2 CH2 COOH greater than Cn greater than Cn CH2 COOH greater than F CH2 COOH, and so on. So you can notice that this NO2 will come after these three cases. Okay, everybody, I hope this part is clear. Okay, next one. If you notice the bromine case here, okay, see, when it comes to bromine, Br uh, CH2 COOH is greater than I CH2 COOH is greater than formic acid, but formic acid is greater than 2 carbon acid COOH here, okay, and then we have Cl here. Then it is formic acid is still going to be greater than benzoic acid. This is slightly greater than benzoic acid, okay, and then pH CH2COOH, and then comes CH3COOH. Again, an extremely important order, very, very important order. All of these are in reference, in NCRT, they were given earlier. So please check it out. Any doubt here, you can ask. Everything is based upon minus I effect here. Next. Next one, if you have only benzoic acid at groups at para position, this is para position groups, and in that groups, I'll directly write the order, okay? So anything which is withdrawing like NO2 is more than chlorine, more than hydrogen, more than OH, OCH3, which is more than OH, like this. This is the order of benzoic acid. Next,
If you have a cis form, that is CH3COOH, compared to a trans form, that is CH3 and COOH, like this, if you have it this way, then the cis form will always be more basic. Keep that in mind. Next, this has to do with, more amount of repulsions observed earlier. After removing of H plus, the repulsions will be slightly lesser. Next, CH3NO2, CH3NO2 directly is more basic than CH3CHO, more basic than CH3COCH3, that is ketone or acetone, which is more basic than CH3CN, which is more basic than CH3COOET. So esters are least basic in these cases. Okay. So from here, I'm sure you got an idea which one is more basic or not. Okay. Now suppose if I gave you this kind of question where I have, you know, uh, benzene being connected here, right, with OH, and benzene being connected here with COOH, benzene being connected here with SO3H, and here it is connected with OH and C triple bond CH. Correct? Here, and I am adding 4 moles of NaNH2. 4 moles. Okay, let me put it this way. 4 moles. Then what is the final product? How does the final product look like? It's a very standard question you should answer. But how does the final product look like? Okay, check this out. In such cases, we need to first understand the acidic strength of all of this. The most acidic one is sulfur group. So that will be released. So you'll get SO3 minus. The second one, most basic, is acid. So that will be released and this will become CO minus. The third one is between phenol, alcohol, and triple bond. In that case, phenols are more acidic, so that will be relieved. And after that, we have alcohol and this one. Between these two, alcohols are more acidic, so that will go plus 4 moles of NH3 here. So this will be the final product. Everybody understood this logic? Then, right, next. Another type of question, which is very standard question that will be asked is, you know, which will be, okay, soluble in aqueous NaOH, and NaHCO3 separately. So number of groups in soluble in NaOH is X, and number of groups soluble in NaHCO3 are Y. So for that case, what is the answer? See, what are the options? How many compounds here? This one, I gave you phenol, cyclohexanol, acetic acid, OH, NO2, OH, NO2, and NO2, OH, NO2, NO2, and NO2. Okay. Next we have OH and OET. Then we have toluene, only toluene, and I have OH, N, and this SO3H, benzoic acid. Okay. So suppose if I take these cases, sorry, other cases CH3NO2 and CH3CN and CH3 COCH3, that is acetone. So let us check these cases. How many X and how many Y? Okay, X. How many X we have? For X, I'll use this green color. Let's see, which all will give. So we know that if NaOH has, if this compound has to dissolve in NaOH, that means they should be able to give H plus, which will create water, which means their pK value should be lesser than water. Whose pK value is lesser than water? First, this one. This one will have lesser than water. Then this one, and this one, 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 this one. Because the pK value for this is 11. That's it. These are the ones which have lesser than water. Remember that all of these will have pK value lesser than water, which means they all will be stronger acids than water. So how many such cases now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 such cases we got. Why? Let me do different color here. This, okay, check. In case of Y, NaCO3. Now they should be lesser than carboxylic acid. Their pK value should be lesser than carbonic acid, which is 6.4. Anything which is lesser than 6, let us imagine. So lesser than 6 is this one, this one, this one, this one, this one, and that's it. These are the ones which are lesser than 6. So how many we got? 5 of them. Done. I guess all of you understood this logic. Then next. Next type of question that could be asked here is that suppose if you have COOH here, NH3 plus here, NH3 plus here, X, Y, and Z are given. Which one is more acidic? So acidic strength will be asked you. Always remember, any ammonium salt will always have less acidic strength than COH. So therefore, Y will be more. And since this NH3 is much, this COH is much closer to this NH3, it will give minus A effect. So Z, then X. Clear on that? Next question. If I was to ask what is the acidic nature of this one? OH with fluorine, okay? So with X, and where X is hydrogen, fluorine, chlorine, bromine, and iodine. In that case, the acidic strength in that case will be, because they will be strongly back bonded, so we will have, iodine greater than bromine, greater than chlorine, greater than fluorine, greater than hydrogen. This will be the order for this case. Everyone understood? Okay. Now let us see ortho effect on carboxylic acid. Ortho effect. That is on benzene, on benzoic acid, any group G is present will, if G is present, it will increase the acidic character, increases acidic strength, so increase acidic strength. Okay. Now Why does it increase acidic strength? This will increase acidic strength due to either SIR effect or due to intra-H bonding. Due to intra-H bonding. These two are the reasons for which it will have better ortho effect. Okay. So let us see some cases now. Suppose I have COOH versus COOH versus CH3 here. Okay. Quickly revise it, guys. Those who are able to do that, those who have an understanding of it, try to answer these questions first. OCH3. Next, NO2. Next, OH. COOH. Halogens X. Third, fourth, fifth, sixth. So quickly do these cases now. In all of them, O, P, M, and H. If you compare all these four, which one is more acidic, which one is less acidic? There, check. First case, CH3. CH3 is donating, so it will decrease the acidic character. So most acidic will be ortho because of ortho effect, and then H, then M, then P. Second case. Again, ortho will be most acidic. Then then ortho will be most acidic. Then you need to check out which is more withdrawing case. So meta is more withdrawing, correct? Then hydrogen, then para. Okay. Next one, you notice NO2 here. NO2 is mostly withdrawing, ortho will be definitely more, then para, then meta, then hydrogen. Next, OH, again ortho effect will be more, this time due to intra-hydrogen bonding. Remember, this is happening due to intra-hydrogen bonding. So O is more, then meta, then hydrogen, then para. Then COH, same logic, ortho will be more, then more withdrawing is at para, then meta, then hydrogen. For case of halogens, ortho is definitely most, then meta, then para, then hydrogen. Because for halogens, you'll only notice inductive effect. This is the order which we need to know. Anybody has a doubt, they can ask me. Yeah? Lastly, if only ortho effect is being given, in all of the cases, suppose ortho effect is observed. Okay. Suppose I have, uh, you know, COOH here and group G here. That means ortho effect is applied by all of them. So if this G is chlorine, bromine, OH, right, NO2 and OMe in such cases, and hydrogen. In such cases, what will be the acidic strength? Okay. Now you will notice, but see, notice carefully, chlorine, bromine, and nitro are withdrawing in nature. OH and OMe are donating in nature. They are all donating in nature. So definitely, these two will have lesser impact of ortho effect as compared to these three. Correct? These three will have more impact of ortho effect. So therefore, acidic character now will be NO2 most acidic, then bromine, then chlorine. Okay, and after that comes OH, then OMe, then hydrogen. So between these two, if you compare, what is the comparison here? Intra H will be dominant over SIR effect when both the effects are giving the same. I mean, OH is also donating, OCH3 is also donating. When you compare two donating, when you compare two withdrawing, in that case, comparison should be always given more priority to intra H compared to SIR effect. Clear on this logic, everybody? A lot of students earlier also they used to make this mistake. So please check this out carefully. If you have COOH and NO2 here, sorry, CH3 here, CH3 here, okay, and you are comparing COOH and CH3 here, correct? Between these two, if you were asked which one is more acidic, okay, then you will go for para. Then you will go for para. Why? Because this is not a benzene ring. Mind you, there is no ortho effect applied. But if the same question has been asked with a benzene ring this time, okay, the minute it is a benzene ring, now ortho effect is applied. So what will be the more acidic character? This one. So be careful about how the structure is. Okay, ortho effect to be applied only on the benzene places, not on the other cases. Clear on that, everyone? I think that's it. These are all the basic acidic and basic stuff which you need to know from this topic. Okay. Mainly anilines are the ones which you need to revise more thoroughly. Okay. Please check out all the amine cases properly. Okay. Uh, I will also discuss. I actually wanted to discuss a lot of PYQs because there are some extremely good PYQs in amines. Okay. So I think I'll leave it for the class. I'll discuss probably in the class today or tomorrow. But make sure that meanwhile you finish all the work. Okay, especially a lot of students have not yet finished the PYQs. Okay, so my suggestion is please complete the PYQ.